Hi, today lecture is Boolean algebra and map simplification. Boolean algebra is an algebra that deals with binary variables and logic operations. So binary variables may be designated with A, B, C, X, Y, Z, etc. So here the operations that we use in Boolean algebra is logic operations. That is and, or, complement, like that. Actually the Boolean function will be expressed algebraically with binary variables, logic operation symbols, parenthesis, equal sign. With this, for example, here f is equal to x plus y complement z. So it's a Boolean expression, Boolean function. So here in this we have x, y, z, three variables, and f is a function. So here f may be either 0 or 1. See, this is an example logic diagram. So what we have seen just now, the Boolean function can be represented as logic diagram. So this is logic diagram. So here the x, y, z are the input variables and f is the output. So this input and output relationship can be represented with the truth table. So this truth table in which f may be 1, so when x equal to 1, and also y equal to 0 and z equal to 1. So this is Boolean function. Actually the Boolean function main purpose is to facilitate the analysis and design of digital circuits. So digital circuits, while the developers are designing the digital circuits, so they want to simplify the circuit, so then they will use this Boolean algebra and express in algebraic form a truth table relationship between binary variables and input output relationship of logic diagrams. So this is the main purpose of using Boolean function, and some rules we need to follow in Boolean algebra. So variables used can have only two values, either 0 or 1. If it is 1 means high and 0 means low. So complement of a variable is represented by a overbar or single quote. Okay, so if b is equal to 0 means its complement value may be 1. If b equal to 1 means its complement value is 0. So ORing of these variables is represented by plus sign, and ANDing of this variables represented with dot symbol. Okay. Laws of Boolean algebra. So some laws we need to use while reducing the complexity of the Boolean function. So we refer these laws as identities of Boolean algebra. Okay. So identities of Boolean algebra: idempotent law, associative law, commutative law, distributive law, identity law, complement law, and involution law. So we use these identities while we simplify the Boolean equations. So as we have in the arithmetic algebra, so this Boolean algebra is also having some laws. Okay, so for example, A and A is A or. So this plus represents or and dot represents and. So A or A is A. Okay, so for example, see, A plus 1 equal to 1 means A or 1 is 1 only, and A or 0 is A. Okay, A and 0 is 0 and A and 1 is A. So this is what laws of Boolean algebra. We use this Boolean algebra laws for simplifying the equation. So how we simplify? So this using this map simplification method. Actually using these laws, identities, we can also reduce directly by substituting these laws, identities into the Boolean expression. Okay, so if you have any given Boolean expression, we substitute wherever A plus A is there. That is A or A is there with the A. And suppose if A plus 1 if it is there in the Boolean expression, we replace with 1. Okay, like this. So we can minimize the minterms in the Boolean expression using these identities. But it is very difficult to identify the minterms. So where we can substitute these identities. Okay, so that process is not clearly defined by anyone. So instead of doing that, so we go for map simplification method. It's a very simple method. So let us see how this map simplification method is used. Okay, so the map method provides a simple, straightforward procedure for simplifying Boolean expressions. So this method may be regarded as a pictorial arrangement of the truth table, which allows an easy interpretation for choosing the minimum number of terms needed to express the function algebraically. See here, this map simplification method is represented as a pictorial arrangement of truth table, and this method also referred as coordinate maps and K maps. So each combination of variables in the truth table is called minterm. Okay, see this is so it's a truth table. So each combination, that is each row, 0 0 0, it's a minterm. 0 0 1 is a minterm. So 0 1 1 is a minterm. So each combination of these variables we refer it as a minterms. Okay, so and the Boolean expression can also be represented as in this format. It's a summation format. Okay, so f is a function and it uses 3 variables and it's a sum of minterms. So this is sum of minterms 1, 4, 5, 6, 7. So wherever we got f value is 1 is 1 minterm. Okay, so 1, it is 1, 4, 5, 6, 7. Okay. See, the map for functions of 2, 3 and 4 variables are shown in the figure. So it's a 2 variable map, it is a 3 variable map and it is a 4 variable map. So 2 variable map we have only 2 variables A and B, and A is changing. A here, A value is 0 here and A value is 1 here, and B value is 0 here and B value is 1 here. Okay, similarly 3 variable map. So A value may be an entire this row of squares. A value is 0. So here it is A value is 1. So similarly column values B, C. It's a B and C. B value is 0 and C value is 0. So similarly 4 variable map. So rows and columns, it's a combination, and each minterm it represents with a numerical value. So we have 2 methods of map simplification, sum of products form and another one is product of sums form. So in this video we will discuss about sum of products form. Later in the next video we will discuss about product of sums. So a Boolean function represented by a truth table is plotted into a map by inserting ones in these squares where the function is 1. So while using this map simplification method, these are the steps we need to follow. Okay, so first we will represent Boolean function as a map. Okay, squares map. So using this map we will insert ones in the respective squares. Okay, see this is a 2 variable map. So this can be represented with this map. It's a and it is a 4 variable map. So in this map we are representing these minterms with ones in the corresponding squares. See, with this we will see one with an example. So map simplification, sum of products. So 3 variable Boolean function it is 0, 1, 3, 5, 7. So this actually will be the Boolean expression with the actual minterms can be represented here. This is a summation representation and it is a actual Boolean function. So here we have 3 variable map. Here we need to keep ones in the corresponding ones squares. So 0, 1, 3, 5, 7. And every square is having value 0, 1, 2, 3, 4, 5, 6, 7. So why this 3 has been changed to this square means, so while representing two adjacent squares, so only one variable must be changed. See, consider these two adjacent squares. So this value is b dash c and bc. So here b value, only one variable is changing. So another variable is same. So consider these two neighboring squares. So here bc, bc dash. So only c is changing, b is as it is. So like this. So this map arrangement will be like that. So every square is changing with only one variable with the neighboring square. Okay, so how to solve this equation? See, this is we have represented 0 here, 0 place 1, and it is 1. Next is 3, 5, 7. And here we need to follow these steps. See, the squares containing ones are combined in groups of adjacent squares. So the ones combined in groups, only adjacent squares. So these groups must contain a number of squares that is an integral power of 2. So while we grouping these ones, so that number of ones grouping must be integral power of 2. That is, either 2 ones must be combined, or 4 ones must be combined, or 8 ones may be combined. That is 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. 2 to the power of 1 means only 2 ones. 2 to the power of 2 means 4 ones must be combined. 2 to the power of 3 means 8 ones must be grouped together. Okay, so only while grouping the ones, so we must consider only integral power of 2's must be combined. And the next step we need to follow is, groups of combined adjacent squares may be shared one or more squares with one or more groups. So if you combine one group, so here it's already combined one, this one is already combined with this one, and again the same one is grouped with another one. That is what again we can share the same square with another group also. So each group of squares represents an algebraic term, and the R of these terms gives the simplified algebraic expression. So one by one we will extract variables from each group. Okay, and Ring of these min terms, we will get the resultant Boolean function. So this let us discuss with one example. See, map simplification, sum of products. So example is given with, it's a function of f and 3 variable Boolean function it is, and sum of min terms, summation of min terms has been given. The same can be represented with the actual min terms with. So first we will represent the map with ones. So here it is 0. So 0th place we place 1. Next 1, it's 1, we place 1. 3, we place 1 here. And 5, we place 1 here. And 7, we place 1 here. And while grouping the ones, so we must consider integral powers of 2. And it should be, so one more thing we need to remember. First we will combine the maximum number of ones first. So next remaining ones will be grouped with the neighboring group also, or individual. So here we got the maximum number is 4 here, 2 to the power of 2. That is 4 neighboring ones we can able to group as a one group. Okay, so the remaining one can be grouped with the previous group also. Okay, so while grouping these ones, we must follow only horizontally or vertically. Okay, so we should not combine the ones diagonally. Okay, so diagonal ones should not be combined together. Okay, so we have 2 min terms here. So how to extract the min terms from this map? So first we consider this group, first group, and first let us see the row side. This A variable, A is changing from A dash to A, that is A complement and A. So the A value is changing 0 to 1 or 1 to 0. So we must eliminate this A value, A variable from the minterm. Why? Because it is changing from 1 to 0 or 0 to 1. Now consider the column. So B dash C, B, C. See, observe this. B value is changing from B complement to B and C is same. So the changing variable must be eliminated. So we will eliminate here one, A is eliminated and B also eliminated. So what has been the resultant variable? So only C. So we keep C here. So so the next group. We consider the next group and see this row. So only one row we have. So A dash as it is we use. And while considering the column variables B dash, B dash C. So here observe this, C is changing. So C is changing from C complement to C. But B is same, B complement. So we eliminate this C value, C variable here, and the B will be considered. So A dash, B dash. So only with the two minterms we got the resultant function. So how many minterms we have in the given equation? 1, 2, 3, 4, 5. So 5 minterms has been given and we have reduced into 2 minterms, 1, 2. So this is how we will simplify using map simplification method. So another example with 4 variable Boolean function. See, we have function A, B, C, D, 4 variables, and the minterms that we need to reduce is 1, 5, 7, 8, 10, 12, 14. So that can be represented with minterms actually like this. Okay, so how to solve this equation? So we have a map, 4 variable map, and each square will be having minterm value, that is 0, that is A dash, B dash, J dash, D dash means 0, 0, 0, 0. So it is a 0. 0, 0, 0, 1. So means 1. So 0, 0, 1, 1. Okay, so 1, 1 means it is a 2 value and 1 value. 2 plus 1 is 3. So like this every square is having a minterm value. Okay, so these values, so wherever these values are there, we keep 1 in the corresponding square. See 1, so first we place 1 here, 5 we place 1 here, 7 we place 1 here, 8 we place 1 here, and 10 we place 1 here, 12 place 1 here, 14 place 1 here. Okay, so we have seen the sequence of steps to be followed. First we will see that the large number of ones, neighboring ones to group. So here first we will see 8 is not there. 8 ones, neighboring ones are not available. So the next smaller one is 4. 4 ones must be combined. So here we got 4 ones. So why? Because this 2 squares are adjacent to the end of these squares. So the entire 4 minterms can be grouped together and form a one group. And the remaining, these 2 we combine with one group, and leftover one also can be grouped to the neighboring group. So we got 3 minterms here. The resultant minterms are 3. So how to extract the equation from this map is, so first let us consider this group, the bigger one. So first row values. So row we have A, B dash, and the column is, so this one and this one. So that is C dash, D dash, C, D dash. 2 column variables, and this is row variables. So observe this, B is changing and A is same. So B is changing from B to B complement. So we eliminate B from this minterm. Only A will be kept. And consider these 2 columns. So C dash D dash C D dash. So here C is changing, C complement to C, but D is same, D complement and D complement. So C will be eliminated. So only D dash will be used. So consider the next group. So consider this is 2 row and only 1 column. So first we consider rows. So A dash B dash A dash B, and the column is C dash D. So observe this, B value is changing, that is B complement to B. So eliminate B, only A dash we will consider, and only 1 column, there is no other column. So as it is we keep C dash D, A dash C dash D. So consider the next group. So row is only 1 and the column is 2 columns. So row is same, so as it is we will keep, and consider the columns. See, observe this, C dash D C D dash. So here C value is changing, so C complement to C, D is same. So eliminate C and keep D here. So this is what the resultant function, A D dash C dash D, A dash B D. This plus symbol represents ORing. Okay, so this is what the map simplification using sum of products. Okay, so in the next video we will see the product of sums method. Good day. Hi.